I see that some of you are still working on these, but that's okay. Let's go ahead and go over them and we'll see how we're doing on them. So for number one, in either case, whether it's a logarithmic or an exponential equation, the first thing we have to do is isolate the logarithm or the exponential. So in number one here, this is the logarithm. We have to isolate that first. So we got to get rid of the 3 that's added and the 5 that's multiplied. So we will subtract the 3, just like solving a regular equation. So we've got 5 times the log base 3 of 2x minus 7 equals 20. And then we'll divide by the 5. So we've got log base 3 of 2x minus 7 equals 4. Now that we've isolated the logarithm, we're going to get rid of the logarithm by using an exponential with the same base. This is a log base 3. We get rid of it by doing an exponential that's a base 3. So 3 to the power of log base 3 cancels out, and we have 2x minus 7. 3 to the power of 4, 3 to the 4th power is 81. Now the log is gone, we're left with simply a linear equation. So we can solve that linear equation. We add 7 to both sides, leaving us with 2x. 81 plus 7 is 88. And finally, we divide by the 2. Get x equals 44. Any questions on that one? Okay, so number 2, this is an exponential equation, but it follows the same sequence to solve it. First thing we have to do is isolate the exponential. That's this piece right here, 4 to the power of 2x plus 1. So we're going to start by adding 7. So 3 times 4 to the 2x plus 1 equals 3,072. Then we still have to get rid of the 3. It's multiplying the exponential, so we will divide by 3. So we have 4 to the power of 2x plus 1 equals 1,024. Now you notice I left a little space in front of the 1,024 because now that the exponential is alone, to get rid of the exponential, the inverse of the exponential is the log with the same base. This is an exponential base 4, so we get rid of it with a log base 4. So the 4 to the power of and the log base 4 cancels out. We have 2x plus 1 equals, to do a log base 4 of 1,024, it's log of 1,024 divided by log of 4. So on our calculator, it doesn't matter whether you use log or ln as long as we use the same one both times. I'll use log 1,024, those parentheses, divided by log of 4, and it's 5. 4 to the power of 5 equals 1,024. So now that we have eliminated the exponential, we are back to a linear equation, and we just have to solve it by subtracting 1. 2x equals 4, and dividing by 3, or divide by 2, sorry. Give us x equals 2. Anybody have any questions there? Anybody get both of those correct? Or would have if I given you enough time? Okay. These are fairly useful equations. In practice, I come from the engineering field, and there's a lot of things in engineering, especially the exponential equations, that are exponential. We didn't get a lot of time to talk about examples, but there's things like, we talked about half-life and stuff like that, but there's charging capacitors and electrical components and things like that that are all based off exponential equations. So to solve them using these logarithms and this exponential logarithmic relationship is very important. If we have time at the end of the class, we might circle back and do some examples of that. for right now, today's topic is kind of a big one, so I want to jump right into it. If you recall, we had equations like this. Y equals 2/3 x minus 1, and y equals negative 1/2 x plus what do I want to do there? Let's go 6. And if I wanted to graph each of those, let's do this one first. Y equals 2/3 x minus 1/2. That starts at negative 1. So that's 0, negative 1 is called the y-intercept. And from there we go up to do the slope of 2/3. We go up 2 over 3 to get our second dot. That's where our line goes. The second one here, y equals negative 1/2 x plus 6. So that starts up here at 6. Technically the point 0.06 is the y-intercept. The negative 1/2 slope, the negative means we go down and then over. We go down 1 over 2 to get our second point. And that line goes through those 2 points. Recall that when we discussed these, what we were saying was this green line was all of the solutions to that first equation. Any point I can find on that line, let's say I pick out the point 0, or this would be 1.50. That would be a solution to that equation. I put 1.5 in for x, 2/3 times 1.5 is 1, minus 1 is 0. That's a solution to that equation. Every point on that line, any point on that line, I make its coordinate and I find its x and y coordinates, those will be solutions to that equation circled in green. And likewise for the equation in blue, that line is all the solutions to that equation. Any point I can find on that, this point here would be the point 12, 0. If I plug that in, I put 12 in for x, negative 1/2 times 12 is negative 6, plus 6 is 0. That's a solution to that equation. What we're going to talk about today is something called systems of equations. Systems of equations involve taking more than one equation and finding values for the variables that satisfy all the equations at once. So what does that mean? Well, we said the blue line is the set of all points that satisfy the equation circled in blue. The green line is all the points that satisfy the equation circled in green. The points that satisfy both of them are right there, where they cross. Where the two lines cross is the solution to both equations. If we graph this very carefully, we would find this point here to be 6, 3. That makes both equations true. Well, this graphing, however, unless you do a very, very precise job, or if you use some sort of technology to graph, can be very imprecise, especially if your solution is not integers like this. 6, 3, those are both integers. They're easy to find on the grid of a graph. But if we had solutions like 1 and 2/3 and the square root of 2 as our answers, those would be very, very tough to find on a standard graph. Even with technology, it'd be tough to get those exact answers. So we know that we can graph those equations and find the point where they cross to solve them. Let's look at algebraic methods to solve them. So let's take these two equations that we just had here. Y equals 2/3 x minus 1 and 1/2 x plus 6. And we know that where the solution to that system is, this y and this y have the same value. They're equal to each other. Of course, you know this x and this x are also equal, but we're going to be concerned about the y's for now. If that y and that y are equal to each other, what they're equal to has to be equal to each other. It's called the transitive property. If this is equal to y and this is equal to y, then they must be equal to each other. This is referred to as substitution. Technically, what I did here is I just replaced the y in one of the equations with the value of y from the other equation. The first equation said y equals 2/3 x minus 1. So I replaced the y in the second equation with 2/3 x minus 1. Now it's just a matter of solving that equation to find a value for x. There's nothing to combine on either side. The variable's on both sides, so I need to get rid of it on one side. So I'm going to subtract 1/2 x. 2/3 minus 1/2, if you found the common denominators, 4/6 minus 3/6 is 1/6 x minus 1 equals 6. And then we add the 1. 1/6 x equals 7. And we solve this. That is something wrong there. That's a negative 1/2. That's where the problem is. Let me go back. I copied my equations incorrectly. This here is not y equals 1/2 x plus 6. It's negative 1/2 x plus 6. So I'll give you time to recopy that. It's 2/3 x minus 1 equals negative 1/2 x plus 6. Changes the tone of things a little bit. Sorry about that. So we still have to get rid of one of the x's, but it's a negative 1/2. So we're going to add 1/2 x. So 2/3 x plus 1/2 x is 7/6 x. We could write it as 1 and 1/6, but we know we're going to have to divide to get rid of it at some point. So 7/6 x minus 1 equals 6. We add the 1. 7/6 x equals 7. And we divide by 7/6. So x equals 7 divided by 7/6 is 6. So we have x equals 6. But that's only half of the solution. The solution to this is going to be an ordered pair. We have a value for x, but we also need a value for y. So knowing that x equals 6, we can come back up to either one of these original equations. I'm going to pick the top one because there's no negatives in it. I just prefer to not work with negatives. So y equals 2/3 instead of x, I'm going to put in 6 minus 1. So 2/3 times 6 is 4. 4 minus 1 is 3. So that's y equals 3. So the solution to this system of equations is the ordered pair. X is 6, y is 3. And you should express it as an ordered pair like that, unless my math lab may ask you to give the values individually. Now, these equations were set up in that graphing format, slope-intercept form, y equals. So it was very easy to put them together. It's not always quite that simple to do. We might have 5x plus y equals a negative 14, and negative 2x plus 3y equals 9. Here, neither of the equations, they're definitely not in y equals form, but neither of the equations is solved for one of the variables. So our first step is going to be to solve one equation for one variable. It doesn't matter which equation or which variable. Generally, however, we try to find an equation that's going to be easy to solve for one variable. What I mean by that is that when we solve for that variable, we're not going to get some ugly decimals or fractions. Here, there's a very obvious variable we should solve for. That's the y in the first equation, because it has no coefficient. It's a coefficient of 1. So when we solve for y, we're not going to divide by anything, so there won't be any decimals or fractions. If we don't have that option to have a divide by 1 or a variable with that coefficient of 1, then we want to look for ones that are going to give us nice, neat decimals or neat fractions, like 2 or 4 or 5. Even 8 isn't so bad, or 10. If I divide by those, I get a decimal that terminates in 1 to 3 decimal places. If I divide by a 3, 6, 7, or 9, those are going to give me repeating decimals. They go on forever, so I'm going to have to express them as a fraction in order to get an exact answer. Fractions are our friends, but we can still avoid using them if we can. So once we have solved one of them for one of the variables, so I'm going to solve that top equation for y. 5x plus y equals negative 14. And I'm going to solve it by subtracting the 5x to get y by itself. So I have y equals negative 14 minus 5x. So I solved that top equation for y. I'm going to call that top equation equation A, the second one equation B. So what we have here is just equation A that's been solved for the variable y. Second step is going to be to substitute into the other equation. So here we solved equation A to get y equals. We now have to put that into the other equation, equation B. We're going to replace the value of y with that. If y equals negative 14 minus 5x in this equation, in equation A, y also equals that in equation B. So equation B becomes negative 2x plus 3 times, replace the y with negative 14 minus 5x equals 9. And now we solve this. Rules of solving linear equations apply. I combine whatever I can on either side. On the left side, I have the parentheses I'm going to distribute. So that negative 2x doesn't change. 3 times negative 14 is a negative 42. And 3 times negative 5x is a negative 15x. This, of course, all still equals 9. Well, there's still more that we can combine here. On the left side of this equation, we have negative 2x and negative 15x. That'll make negative 17x minus 42 equals 9. Now we have combined everything that we can combine. So we have a simple linear equation. So we're going to go ahead and solve this simple linear equation. We're going to add 42 to both sides. So a negative 17x equals 9 plus 42 is 51. Then we'll divide by a negative 17 to get x by itself. X equals negative 3. Now again, we're only halfway to the answer. X equals negative 3, we still need to know y. Now, I could go back to one of the original equations, but I can save myself a lot of effort if I come right to here. I have this equation already solved for y. So if I put -3 in for x, I can very quickly calculate y. Now I have to be very careful here with the signs. Of course, the -14 isn't going to change right now, but I'm going to treat this as a -5 times a -3, which will be a +15. Then for y equals -14 plus 15 is a +1. So y is +1. So our solution there is x is -3 when y is 1. Any questions there? I'm going to have you guys try one. Three x plus 2y is 16. X minus 3y is -13. I'll give you guys a couple of minutes on that, and then we'll go over it. So we have to pick one of these to solve for one of the variables. I'm going to label them equations A and B just for quick reference. I'm going to solve equation B for x. So I'm just going to add 3y. So x equals -13 plus 3y. Or you could have written it as x equals 3y minus 13. Either one would be appropriate. Now I need to substitute that back into the first equation, equation A, for x. So 3 times -13 plus 3y plus 2y equals 16. I distribute the 3, giving me -39 plus 9y plus 2y equals 16. There's still more I can combine on that left side, 9y and 2y. So the -39 doesn't change. 9y and 2y is 11y equals 16. Now we have a simple linear equation, so we're just going to solve. We're going to add 39 to get rid of the -39. 11y equals 55. And we'll divide by 3 to get y equals 5. So again, that's only half the answer. We can plug back into one of the originals, but I already have equation B here solved for x, so I'm going to plug that 5 in for y there. So x equals -13 plus 3 times 5, which becomes -13 plus 3 times 5 is 15, which becomes -13 plus 15 is 2, so x equals 2. So the solution there is x equals 2 when y equals 5. So that's the substitution method. The next method we're going to look at is called the addition or elimination method. Depending on which textbook you're using, it goes by either name, addition or elimination. And it goes off of the properties, the addition property of equations, of equality. If I have an equation like 2x minus 7 equals 21, I can add the same thing to both sides. I can add 7 to both sides, and it doesn't change the equation, which we've done this a lot. 2x equals 28, and we divide by 2 to get x equals 14. Now, if we knew x equals 14, I could have subtracted x from one side and 14 from the other. I am still technically subtracting the same thing from both the left and the right side of the equation. It's in a different form, but since x equals 14, they're the same value. So 2x minus x is just x, minus 7 is still there. 21 minus 14 is just 7. What I have here is an equivalent equation. I add x, or add 7, I should say, x equals 14. So I haven't altered that equation. Well, in our systems of equations, so let's do something like this. 2x minus y equals 9, and 3x plus y equals 6. I'm not going to solve one of the equations because they have two variables. But I do know this equation B tells me that 3x plus y is equivalent to 6. So what that means is I can take the first equation and I can subtract 3x plus y from one side, or add 3x plus y to the one side if I want to, and I can add or subtract 6 to the other side, as long as I do the same to both. So since 3x plus y equals 6, I'm going to add 3x plus y to the left side of equation A, and I'm going to add 6 to the right side of equation A. So 2x minus y plus 3x plus y. Well, the 2x and the 3x make 5x. Negative y and positive y cancel out. It's gone. Equals 9 plus 6 is 15. So it's called the addition method in some textbooks because we're adding the same to both sides of one of the equations. Or the elimination method because it eliminated the y variable. It's now gone. We have an equation just in terms of x. We solve it by dividing by 5. Get x equals 3. Now we do still have to go back and solve for y. It does not matter which equation we use. I'm going to use the bottom equation because there's no negatives in it. So 3 times, I'm going to replace x with 3, plus y equals 6. I combine what I can here. 3 times 3 is 9, plus y equals 6. I subtract 9 from both sides. Y equals negative 3. So x equals 3, y equals negative 3 is the solution to that equation. Now that equation worked very simply because I have negative y in one and a positive y in the other. They canceled out automatically. They were all set to do that. That's not always the case. Sometimes we have to force the issue. So I might have an equation like 3x plus 5y equals 1. 2x minus 3y equals 7. Once again, for ease of reference, I'm going to label them equations A and B. Right now, if I added those equations together, nothing is going to be eliminated. Nothing's going to disappear, cancel out. So we have to force the issue. What we're going to do is we're going to look at the coefficients of both variables, and we're going to think in terms of least common multiple, very much like least common denominator for fractions. So for x, I have coefficients of 2 and 3. Their least common multiple is going to be a 6. So I could turn my x's into 6's. For my y's, I have 5 and negative 3. Their least common multiple would be a 15. Notice the negative doesn't affect that at all. So I could turn both of the y's into 15s to eliminate one of those. Now the key is I want one to be positive and one to be negative. Here, the y already has one positive and one negative, so that works in our advantage. But I don't want to go with a number as big as 15. We could, and it would work just fine, but I'm going to prefer to work with smaller numbers. I'm going to eliminate the x by turning them both into 6's. To do that, I am multiplying the complete equation. So equation A, I'm going to multiply by 2, because 2 times 3x is 6x. That turns it into a 6. I'm going to multiply equation B, not by 3, because 3 times 2x would be 6, but by a negative 3. Because not only do they both have to be 6, but one has to be positive and one has to be negative so that they'll cancel out. So now, bring equation A down here. 2 times equation A, 2 times 3x is 6x. 2 times 5y is 10y. Equals, I have to remember to multiply the constant on the other side as well. 2 times 1 is 2. So that is 2 times equation A. Equation B, I'm going to do negative 3 times equation B. Distributing the negative 3. Negative 3 times 2x is a negative 6x. Negative 3 times negative 3y is a positive 9y. Equals, negative 3 times 7 is a negative 21. Now this is set up so that if I add the left sides of my equations and the right sides of my equations, the x will cancel out. 6x and negative 6x cancel out, adds up to 0. 10x and 9x is, or 10y and 9y is 19y. 2 and negative 21 is a negative 19. So we have 19y equals negative 19. We'll solve that by dividing by 19 to get y equals a negative 1. So we have y as negative 1. We still have to go back and find x. We do that by going back to the first equations. I'm not going to go back to the ones I multiplied because those are more complicated. But I have y equals negative 1. It really doesn't matter which one I use, so I'll just pick the top one. 3x plus 5 times negative 1 equals 1. The 3x doesn't change right now. 5 times negative 1 is a negative 5 equals 1. So now I'm going to solve that by adding 5. 3x equals 6. And I divide by 3. Get x equals 2. So my solution here, x is 2 when y is negative 1. Any questions on those examples? So I'm going to give you a few minutes to try one of those on your own. So I have 3x minus 2y equals negative 12. 5x plus 3y equals, oops, sorry, got that wrong. Should be a negative 1. Go ahead and use the addition or elimination method to solve that system of equations. We'll go over it in just a minute. Obviously, they won't cancel the way they are, so we have to pick a variable. I'm going to go with the y. So I'm going to multiply the top equation by 3, a by 3, and equation b I'm going to multiply by 2. So it's going to give me a negative 6 and a positive 6. So equation A, 3 times equation A is going to give me 9x minus 6y equals a negative 36. 2 times equation B is going to give me 10x plus 6y equals negative 2. So we're ready to add those equations. 9x and 10x give me 19x. Y's disappear equals a negative 38. Dividing by 19 gives us x equals negative 2. We have to go back and find y. So I'm going to pick this bottom equation here. 5 times, I'll put negative 2 in for x, plus 3y equals negative 1. Now I could have picked either equation. I just always try to pick the one with the least negatives on the variables, just because it usually produces less calculation errors. So 5 times negative 2 is a negative 10, plus 3y equals negative 1. We will add the negative 10, or add 10, I should say. You get 3y equals negative 1 plus 10 is 9. And we divide by 3 to get y equals 3. So x is -2 and y is 3, where those equations cross. We can run into equations like this. Two x minus 3y equals 7. -4x plus 6y equals 20. When we go to solve this one, I notice that I don't have to multiply both equations. If I just multiply the top equation by 2, the x will cancel out. So let's do that. 2 times equation A gives me 4x minus 6y equals 14. I'm going to leave equation B just the way it is, so I'm working now with those two equations. However, when I go to do my addition here, -4x and +4x cancels out, but so does +6y and -6y, leaving me with 0 on the left side. On the right side, 20 plus 14 is 34. 0 does not equal 34. That is never true. What that means is that this system of equation has no solutions. If I were graphing these equations would look something like this on the graph. They would be parallel. So they're parallel lines, they never cross, so they never have a point that is a solution to both equations. Similar to that, I can have equations like this. 5x minus 2y equals 4, or negative 10x plus 4y equals -8. Here I notice equations A and B. If I multiply equation A by 2, equation 2A gives me 10x minus 4y equals 8. So now I'm working with equation B and then my 2 times equation A. When I add those together, everything cancels out. -10x cancels out. 4y and -4y cancels out. So I have 0 on the left side. But I have -8 and +8. Add the 0 on the right side as well. That is always true. So what that means is the solution is any point on either equation. So I can just write down one of the equations. 5x minus 2y equals 4 is the solution to that system. What that is saying is if I graphed those lines on the graph, not only are those lines parallel, but they're the same line. This type of an equation is what we call dependent. In other words, they're the same equation, they're the same line, just different forms of the same equation. This type of a system over here is what we call inconsistent. The lines don't cross, so there is no solution to that system. Okay, it is actually slightly past break time. It's 10:22. So let's take our break and let's come back at about 10:30, and we will start with 3 variable systems of equations. So for the second hour here, we're going to talk about 3 variable systems of equations. For 3 variable systems, graphing is really not a good possibility, at least not without technology. We can graph a 3 variable equation, but it gets really tough to do. Just to plot a point in 3 variables So just to plot an XYZ coordinate, we first have to define the XYZ plane. So the XY plane on a flat piece of paper, if we're looking at it from above, looks like that. Well, when we're going to add the Z plane, we have to not only look at it from above, but if we look at it from directly above, Z is coming straight out at us. So we have to kind of look at it from off to the side, but still above. So when we're doing that, the XY plane looks something like that. And then the Z axis pops up or down out of the middle of that. So just to plot a point like 2, 3, -1. So that's saying x equals 2, y equals +3, and z equals -1. To show that point on the graph, we basically have to make a box on the graph going to that location. Where this opposite corner, here's the origin right here. The corner that's opposite the origin is the point we're trying to plot. Now you can see without that box on there, knowing that that point was x equals 2, y equals 3, and z equals -1, that would be impossible to see. It's even hard to see with it drawn out. Let me draw the lines in solid instead of dotted for you. So you can see there's the box. The origin is this corner. The point we're plotting is that opposite corner. Very tough to visualize. So trying to get 3 lines to cross, and it's not even lines, it'd actually be 3 planes when we're talking in the 3 coordinates, because a single equation doesn't give a line, it gives a plane. Trying to graph that would be extremely difficult. So we don't do graphing as a solution. So we're down to our 2 algebraic solutions, substitution and elimination. So let's do substitution first. So I'm going to label them A, B, C. And for substitution, just like all the others, just like 2 variables, step 1 is to solve 1 equation for 1 variable. Helps if I put my E in my 1. So I'm going to pick equation B. So I'm going to solve equation B for the variable x. So I'm going to do that all in one step. I'm going to add the 2y to both sides, and I'm going to subtract 2z from both sides. So what I get there, my new equation B is x equals 9 plus 2y minus 2z. That is my modified equation B. It's been solved for x. Step 2 now is to substitute into both other equations. There isn't just one other equation here, there's 2. And we have to substitute that solved equation into both of them. So we're going to substitute it first into equation A. So 2x becomes 2 times, instead of x, we're going to use 9 plus 2y minus 2z minus 5y minus z equals 9. And now, of course, we have to simplify this. And what we're going to get is an equation that now only has 2 variables in it. I'm going to distribute the 2, giving me 18 plus 4y minus 4z minus 5y minus z equals 9. And then we're going to combine. I'm going to combine 4y and negative 5y to make a negative y. Negative 4z and negative z to make negative 5z. And I'm going to subtract 18 from both sides to get rid of the constant on the left side. 9 minus 18 is negative 9. So there is my modified equation A. Negative y minus 5z equals negative 9. Now, all of those are negative. I could rewrite it by multiplying the whole equation by a negative 1. So instead of negative y minus 5z equals negative 9, I could have y plus 5z equals positive 9. But I don't know if I'm going to want it that way yet. We have to find what equation C is going to become yet. We still need to substitute this equation B that we solved for x into equation C. So that'll be 3 times instead of x. I'm going to put in 9 plus 2y minus 2z plus 2y plus 3z equals 13. So let's multiply by the 3. Distribute the 3. So we've got 27 plus 6y minus 6z plus 2y plus 3z equals 13. So again, I'm going to combine the 6y and the 2y makes 8y. Negative 6z and 3z make negative 3z. And I'm going to subtract the 27. 13 minus 27 is a negative 14. So there's my modified equation C. What I have now is 2 equations in 2 variables. So I've reduced my 3-variable system to a 2-variable system. 3 variables with 3 equations down to 2 variables with 2 equations. So this new system is equation A is, I can use the positive version, I guess, y plus 5z equals 9. I'll use the positive version. And equation B is 8y minus 3z equals negative 14. I have to solve that system somehow. I'm going to do it by solving equation A for y. So I'm going to take equation A here. Y plus 5z equals 9. And I'm going to subtract 5z to get y equals 9 minus 5z. So now I have to substitute that back into the other equation. So B becomes 8. Instead of y, it's going to be 9 minus 5z minus the 3z equals a negative 14. Now we combine what we can on each side. So I'm going to distribute the 8. 8 times 9 is 72. 8 times negative 5z is a negative 40z minus 3z equals a negative 14. Still have more that we can combine there. Negative 40z and negative 3z makes a negative 43z. Still have the 72, and this equals a negative 14. So now we're going to solve. So we'll subtract 72 from both sides. Negative 43z equals a negative 86. And we're going to divide by negative 43. Z equals, this is a negative 86, by the way. Z equals a positive 2. Negative 86 divided by negative 43 is 2. So we have Z. Now we still need to find both y and x. So I'm going to work my way back through. If I go back one step, here I have a system of two equations with two variables, y and z. So if I know z, I can find y. In fact, I have this equation solved for y already. So I can put that 2 in there for z and get y rather quickly. So y equals 9 minus 5 times 2 becomes y equals 9 minus 10, which gives us that y equals -1. So now we have z and y, we can go back to find x. Going all the way back up to here, I had equation b solved for x, so let's put those values in there. X equals 9 plus 2 times y is -1 minus 2 times z is 2. So 2 times -1 is -2. -2 times 2 is a -4. 9 minus 2 is 8, minus 4 is 4. Oops, sorry, 9 minus 2 is 7, minus 4 is 3. So x equals 3. So the solution to that system, x is 3, y is -1, and z is 2. 3, -2, or 3, -1, 2. Can't make my mouth work today. That's a very long process. And obviously, I'm not going to do a ton of examples of solving a three-variable system. What I am going to do is I'm going to take that same system that we had. Maybe I'll take a different one. It doesn't matter. Easier to take a different one at this point. And we're going to solve this system using a different method. The method we're going to use is the elimination or addition method. So we're going to take an equation like let me catch up with my thoughts here. So addition or elimination method. So my equation is going to be 2x plus y minus 3z equals -2. X plus 3y minus 2z equals -5. 3x plus 2y minus z equals 7. So once again, I'm going to label them equations A, B, and C. To do the elimination method, I have to pick one variable that can be eliminated in two different equations. So looking at this, there aren't any that are really going to be easy to eliminate. In fact, they're all pretty much about the same difficulty. They all have coefficients of 1, 2, and 3, or -1, -2, -3. So I'm just going to pick a variable. I'm going to pick x. We're going to eliminate x. So now it says I have to eliminate it in two equations. So what I'm going to do is I'm going to use one equation to eliminate x in the other two. So I'm going to use b. Since b is just that one x or just the x, it's going to be a lot easier to use that to eliminate x in the other equations. So I'm going to start out with equation A, which is 2x plus y minus 3z equals -2. And what I'm going to use with it is -2 times equation B. So if I multiply equation B by -2, -2 times x is -2x. -2 times 3y is -6y. -2 times -2z is +4z equals -2 times -5 is 10. And the reason I've done that is now the x will be eliminated when I add the equations. 2x and -2x out. Y and -6y is a -5y. -3z and +4z is a +1z or just +z. -2 and 10 make +8. So there, I'm going to call that equation A, even though I've used B to eliminate the x. That's my modified equation A. -5y plus z equals 8. So I need to do equation C now, which is 3x plus 2y minus z equals 7. And I still need to use equation B, but this time I'm going to use -3 times equation B. So -3 times x is a -3x. -3 times 3y is a -9y. And -3 times -2z is a +6z. And -3 times -5 is a +15. So now when I add these equations, the x again is eliminated, which is good. I wanted to eliminate the same variable both times. I eliminated x both times. So 3x and -3x cancels out. 2y and -9y is a -7y. -z and +6z is a +5z. And 7 and 15 is 22. So that is my modified equation B. So I'm going to use those two equations as a system. And what I'm going to do is this. I'm going to take -5 times equation A. -5 times -5y is 25y. -5 times z is a -5z equals -5 times 8 is -40. The reason I did that is because now if I take equation B, -7y plus 5z equals 22, I see that the -5z and the +5z are going to cancel out. So I add these equations. 25y plus -7y is 18y. -5z and +5z cancel out. Equals -40 plus 22 is a -18. So 18y equals -18. I divide by 18 to give me y equals -1. Now that we have y, we have to go back and find values for x and z. Well, my previous system here is in terms of y and z, so I'm going to find z next. I'm going to use this version here of equation A. So -5 times y becomes -5 times -1 plus z equals 8. We combine -5 and -1 to make +5 plus z equals 8. And I solve for z by subtracting 5. Get z equals 3. Now I can go back to one of the original equations to find x. One of those original equations, equation B, was x plus 3y minus 2z equals -5. So I'm going to use my values for y and z here. Y is -1, so I got the x. 3 times y becomes 3 times negative 1, minus 2 times z becomes minus 2 times 3 equals negative 15. Three times negative 1 is a negative 3. Negative 2 times 3 is a negative 6 equals negative 15. Oops, not negative 15, it's negative 5. I don't know where that 1 came from. So equals negative 5. Negative 3 and negative 6 make negative 9, so that's x minus 9 equals negative 5. And I'm going to solve by adding 9 to both sides. So negative 5 plus 9 is 4. X equals 4. So my solution here is 4, negative 1, 3. Now I realize I only did one example of each of the forms for the 3 variable equation. Is there anybody that has not seen 3 variable systems or has a lot of questions on the process for the 3 variable systems? Those questions are just so time consuming. It is tough to do more than a couple of examples. So I wanted to make sure I saved time for doing some problem solving, some word problems. So if I want to do problem solving with these, there's a lot of different things that we can describe. We might describe a triangle. And in this triangle, the measure of the largest angle is 55 degrees larger than the smallest. So if I let my triangle have angles x, y, and z, if I let z be the largest, and x be the smallest, this is telling me that z equals x plus 55. Well, it's not enough information quite yet, so let's see what other information we can get here. We might also be told the remaining angle is 35 degrees. So the middle angle is 35 degrees larger than the smallest. So y is the middle angle. So y equals x plus 35. So we know from our basic rules of geometry, x plus y plus z equals 180 degrees. Here's a system of equations, and this is a 3 variable system. We've got equation A, B, and C that is tailor-made for substitution because A and B are both already solved for a variable. So I can substitute both of those into equation C. So for equation C, it's going to become x doesn't change. Y, however, we're going to put in x plus 35. And for z, we're going to put in x plus 55 equals 180. And now we do our combining and solving. On the left side here, we have x, x, and x, which makes 3x. 35 and 55 makes 90, and that equals 180. So we'll solve by subtracting 90. So 3x equals 90, and we'll divide by 3. Get x equals 30, or x equals 30 degrees. So our smallest angle here is 30 degrees. Now, I didn't really ask a question here, but I implied that I was looking for all three angles. So I have to go back and find the others. Angle Z equals x plus 55. So 30 plus 55 is 85 degrees. So Z, 85 degrees. Y equals x plus 35. So that's 30 plus 35 is 65 degrees. So Y is 65 degrees. Well, that's a relatively simple example of a system of equations. Let's look at an example that's only two variables, but still a little bit more complex. This is a geometric application, actually a construction application, called the dual slope truss. This type of a dual sloped intersecting surfaces happens a lot in construction, mechanical design, engineering, landscaping, and things like that. So we have two intersecting surfaces. In this case, it is a building truss. And the slope on either side coming up to it is different. On one side, that symbol means it's a 15 and 12 slope. 15 units a rise for 12 units a run. On the other side, it is a 3 and 12 slope. The full span of this truss is 36 feet. We want to know what's x, what's y, and what is the height of this truss. This is what we call a wireframe, by the way, so we're assuming no thickness to the members so that we can just do the line geometry here. So what are some things that we know? Our first equation, equation A, I know that x plus y has to add up to 36. My second equation is going to deal, my second and third equations are going to deal with the slopes. Equation B, I'm going to deal with this over here. This is a rise of 15 for a run of 12. If I rewrite it like this, it'll make a little more sense. That compares to h over x. 15 over 12 is the same ratio as h compared to x. We're going to come back to that in a little bit. My third equation deals with the other side over here. I have my 3/12 slope, rise of 3 for a run of 12. Again, I'm going to redraw it like that so that you can see how it matches up a little better. So that 3 out of 12 slope is going to equal to h is the rise that goes with the 3, and y is the run that goes with the 12. So I have my three equations. It's time to try to substitute. What I'm going to do is I'm going to try to substitute for values of x and y into equation A. Try to get them both in terms of h so that I only have one variable. So if I look here at equation B, if I cross multiply, 12 times h is 12h. 15 times x is 15x. If I solve that for h by dividing by 15, sorry, not by 15, by 12, it's 12h. I get that h, 15 over 12 is 1 1/4 x. Or I could write it as 5 fourths x. Let's do the same with equation C here. So I'm going to cross multiply. 12 times h is also 12h. 3 times y is 3y. And once again, I'm going to divide by the 12. To get h by itself. Well, h equals 1/4 y. Now, if I look at that, if I try to substitute them back into the equation, that's not going to work out so nicely. I have x and y, not 1 1/4 x and 1/4 y. So what it tells me is I solve these the wrong way down here. I want to get just x. So what I should have done is divided by the 15 to get that x is equal to 12 over 15 is what is that? 4, that's 0.8 h. Dividing by 3 here would give me that y equals 4h. So now I have x in terms of h, and I have y in terms of h. So I can go back to my original equation up here, x plus y equals 36. X is 0.8h, y is 4h. 0.8h plus 4h equals 36. So let's bring that down here and work with it. So 0.8 and 4 make 4.8h equals 36. And we will divide by 4.8. To get h equals 7.5. So what that's saying is h is 7.5 feet tall. To find x, we know that x is 0.8 times h. So 0.8 times 7.5, 7.5. That's going to give us, what is that, 6? So x is 6. Now at this point I could just subtract from the 36 to get y, but let's double check it. Y equals 4h, so 4 times 7.5, which is 30. So it does work out. 30 feet and 6 feet add up to 36 feet. So you can see in real life, the systems are not as cut and dried as the ones we're used to looking at. The systems can take on a lot of different forms. In this system, 2 of our equations, rather than being written out linear like this, they were written out as proportions. So we had to cross multiply to get the linear equivalent of those proportions. Let's say we're asked to find a quadratic equation through the points my first point is going to be 1, 3. My second point is going to be 3, -1. And my third point is going to be 4, 0. Now, a quadratic equation takes the form of y equals ax squared plus bx plus c. We're used to having a system of equations where it's x, y, and z that we're looking for. In this case, we're going to have values for x and y. What we're going to be looking for is values for a, b, and c. So for our first equation here, for a first point, I should say, we know that x is 1 when y is 3. So y is 3 equals a times 1 squared plus b times 1 plus c. For the second point here, we have x is 3 when y is negative 1. So negative 1 goes in for y. A times x is 3, so this is 3 squared, plus b times 3 plus c. And for the last one, 4, 0, y is 0, x is 4, so it's a times 4 squared, plus b times 4 plus c. So I can rework these equations slightly. This first equation is going to be 1 squared is just 1, so that's just a. B times 1 is just b, plus c equals 3. Notice I put this at the end of the equation instead of the beginning, because we're used to seeing it that way. Next here, a times 3 squared, that's 9, so that's 9a, plus b times 3 will be 3b, plus c equals negative 1. And the last one, 4 squared is 16, so that's 16a, plus 4b, plus c equals 0. So there's my system I'm going to work with. Call those equations A. I don't want to call them A, B, and C because I already have A, B, and C here. Let's call them equation 1, 2, and 3. And you'll notice that we can eliminate the C really easily. So what I'm going to use is I'm going to take equation B here, or 2, I should say, 9a plus 3b plus c equals negative 1. And I'm going to combine it with negative 1 times equation 1. So that becomes negative a plus negative b plus negative c equals negative 3. So now when I add those equations, 9a minus a is 8a. 3b minus b is positive 2b. C minus c is gone equals negative 1, negative 3 is negative 4. So there is one of my equations. I'm going to do the same with equation 3. So 16a plus 4b plus c equals 0. I'm going to combine it with negative 1 times equation 1. So it'll be negative a, negative b, negative c equals negative 3. And when I add those together, (16a) and negative a make 15a. 4b and negative b make 3b. C and negative c cancel out. 0 and negative 3 make negative 3. Both of these equations that I have here can be simplified some. This first equation, I'm going to multiply by 1/2. It's the same as dividing it by 2. The reason I'm going to do that is I noticed every coefficient in there can be divided by 2. That gives me 4a plus b equals negative 2. It's just a much simpler equation to work with. This one over here, I'm going to multiply by 1/3. That's the same as dividing everything by 3, because I noticed every coefficient there was divisible by 3. Gives me 5a plus b equals negative 1. Now with those two equations, it's going to be a lot simpler to solve the rest of the system. I'm going to multiply this first one by negative 1, so I'll get a negative 4a minus b equals 2. And I'm going to add these equations. 5a and negative 4a make a. B and negative B cancel out. Negative 1 and 2 make 1. A equals 1. So I'm going to substitute that back into one of these previous equations. Let's do this one here. So 4a becomes 4 times 1 plus b equals negative 2. 4 times 1 is just going to be 4 plus b equals negative 2. I will solve that by subtracting 4. To get b equals negative 6. And then I had one of my original equations, my first one actually, equation 1, was a plus b plus c equals 3. So a is 1, b is negative 6, plus c equals 3. I'll combine 1 and negative 6, give us negative 5, plus c equals 3. I add 5. To get c equals 8. So a equals 1, b equals negative 6, and c equals 8. But remember, our form was y equals ax squared plus bx plus c. So that's telling us our equation is y equals 1x squared is just x squared. Negative 6 for b, so that's minus 6x. And c is 8, so plus 8. So there is our quadratic equation. Okay, only 6 minutes left, so we don't really have time to do another example. Remember, there's an old homework from Monday that'll be due Thursday. Then a quiz on that homework from last week, Wednesday, and last Monday will be due Friday. Then there's going to be a new homework that'll be due next week, Tuesday. Remember, by the way, you'll be looking through your tests, redoing the questions you got wrong. You still have another week to turn in those test corrections if you want to. If you're not sure how to redo a problem, you can talk with a classmate, you can talk to me, you can talk with somebody else that you know that's good at math and work through them and turn them back in to get back up to half your points. So if you ended up with a 70 on that test, getting half your points back would put you at an 85. Then, of course, there's still that test correction. The 2 questions I gave you back for not being fair questions. So that would turn that 70 actually into a 92 if you did corrections on it. Anybody have any questions? Okay, well, you guys have a great weekend, and we'll see you all on Monday.